Okay, today I'm going to derive some mathematical equations for least square method. Least square method is a very popular mathematical method which is used in many engineering problems. It can be summarized using this equation. A transpose times A times X equals A transpose times B. Don't worry, we will derive everything and arrive at this equation at the end of this video. Before I start, let me give you a motivating problem to solve. So assume that we have a x and y coordinate system in which we have several points distributed like so. And your task is to fit a line using these points so that the distance from the point to the line is minimized. So in the end, you may end up a line something like this. And by distance to the line, I mean the y distance. So now indicated by the green line over here. Right. Let's formulate it. So the line can be written in this following term: y equals a0 x plus a1. And if we plug in one of the points into this equation, then we have, but let's first define the points. So we will name our sample points xi, yi, and the I is ranging from 0 to n. So we assume we have n plus 1 points. And for example, this guy will be y0, x0, y0, and this guy will be x1, y1. So if we plug any of these points into the equation, we have yi equals a0 xi plus a1. But if you are checking it carefully, this equation actually doesn't hold, because what's missing in between is the error that is between the point and the line. Okay, so since we're interested in the error term and we want to minimize it, let's bring it to the left side of this equation, which brings us this one. And actually we want to sum over all the errors, because we don't want to just calculate one error, but we want to have all the errors. Right. But now you will see a problem. If we simply do this calculation here, we may introduce some positive errors. For example, for the point x0, y0, and for the x1, y1, we may introduce some negative errors, and those errors will cancel out, and that's not what we want. What we actually want is the squared error, so that we have all the errors positive when summing them up. One might argue that we can also use the absolute value of the errors. That's correct, but for least square method, if we use the square, it will help us in the following mathematical derivation. To be more specific, it helps. It's much easier to do derivation over the squares than the absolute operator. Okay, so now we have arrived the equation to calculate the sum of the squared errors. Let's try to write this formula in the matrix form so that we can use the toolbox from our linear algebra to help us get a more compact solution. Okay, how can we do that? So if you look at here, this guy is actually a dot product of this row vector here and this column vector. It's exactly equivalent. So let's write it still. And what else can we do? We are summing over the i's. So what if we expand it simply? So this is an x0, 1, x1, 1, 2, xn, 1. And here nothing changes, still a1, a0, a1. And here is y0, y1, till yn. And don't forget the square over here. But now we have expanded our equation into a matrix and a matrix calculation, but in the end we will get a column vector instead of just one value. What we are missing here is we actually need to sum all the values of the rows so that we will get the same result like before. Okay, to simplify the notation here, let's call this guy B, and this guy here A, and this A0, A1 is actually the unknown that we are trying to solve, so let's call it X. Okay. Now we have B minus A times X to the power of 2. Now it's very compact, but I want it to be more compact. I want to get rid of this summation over the rows. And let's look at this guy more carefully. So, as we said, this guy is just the row, column matrix. And if we write out its values, it's actually something like this. And we want to do the square of each element of it, and then we also want to sum over the rows of it. In the end, we have a scalar, and this operation is exactly equivalent to this one here. So it's simply the transpose of this column vector times itself, a dot product, and then we get the same value So let's rewrite this guy. The transpose of it times itself. Beautiful. Now we can use some tricks that we learn from our linear algebra. For example, let's take the transpose into the values inside the parentheses. Then we have B transpose minus X transpose times A transpose. Naturally, we apply the distributive law. And continue on the second part. Right. So, this one and this one actually is the same. Why? Because in the end, we're just calculating the error term, and the error term is actually just a scalar. And so for no matter B transpose B or B transpose times A times X, they all end up into a scalar. And for this two terms in the middle, it's either calculating from the first B times A and then times X, or the reverse way, X times A times B. They in the end end up with the same value. So let's combine them. So I will take the one term which do not have the X transpose. So we have this one 2 times B transpose AX plus X transpose A transpose AX. Well. Now we have reached a very beautiful equation. It looks very similar to its 1D counterpart, which is this thing here. If you ignore its matrix property, this is just a quadratic function. And we learned that if you just consider this guy in the 1D case, and this guy will look like something like this. And how do we find the minimum of it? We just find the derivative of this guy and set the derivative to 0, and then we find the corresponding x value, which is this one. So and how can we say that it is the local minimum instead of a local maximum? Because this matrix here, namely A transpose A, is a semi-positive definite matrix. It gives us a nice property that in most of the cases it will have a local minimum. Here I say most cases because there are some corner cases where this assumption doesn't hold. But in our example, this will work. Okay, as we said, we want to calculate the derivative of this guy. So let's call our function fx, and what we want to do is we want to calculate the derivative of fx over x, and we want to set the derivative to 0. Okay, before we do that, first let me introduce two rules which will help the derivation. So first rule is so the derivative of B transpose times X is B. And second rule is how to calculate the derivative of this guy. And it is actually H plus H transpose times X. Okay, now let's try to derive our derivative equation. So first, B transpose B, it has no X in it, so it's 0. And then the second term, we will use rule number 1. Then we will get 2 times A transpose B. And then the last term, we will use rule number 2, which will give us A transpose A plus A transpose A whole thing transpose times X. Since A transpose times A is a symmetric matrix, doing the transpose of it again, it's just the same as itself. So let's write it down. It's 2 times A transpose A times X. And set it to 0. So we can move the negative part to the right. Of course, we can get rid of the 2. Then we have A transpose A X equals A transpose B. This is exactly the least square equation that we introduced at the beginning of this video. Let's look back. What does each symbol means? So A is just a matrix consisting of the X coordinate of all the points plus a vector of 1. And then B is just the column vector consisting of the Y coordinates. And X is the one that we try to solve. And since we reach here, we just need a final step, which is solving X. And that becomes very easy. The straightforward way is to calculate the inverse of A transpose A and then multiply to the left side of A transpose B. And then you get your X. And you get the equation of the fitted line, which has the least squared errors between the points and the fitted line.